In previous videos, I've worked out what the effect would be of a charged particle, which has now been put into an external magnetic field. You could calculate the precession frequency. We also worked out the quantum mechanical um, case of which gives you basically the exact same equation, that the energy that it takes to align this particle you can calculate as minus the magnetic moment dotted into the magnetic field. And then all you have to do is just turn the magnetic moment into a quantum mechanical operator. And when we did that, what we got was the Bohr magneton, which was the charge times h bar over 2mc, which I worked out was 0.6 times 10 to the minus 8 electron volts per Gauss for the electron, and 0.3 times 10 to the minus 11 electron volts per Gauss for a proton, let's say. And you can see, the difference is that there's a much larger magnetic effect on the electron because the electron is at a larger radius. So the nucleus, or the proton, is just sitting here spinning around its radius, and the electron is way out here spinning around a much larger orbit, and so it's going to have a much larger magnetic moment. And then depending on what the energy level is, then we can just multiply if we were to take this, we would end up with ml, depending on what state it is, times this Bohr magneton. And then we're operating on a state, of course. Which just means now that you would get, m's of L's 1, 2, 3, depending on what orbital you're in. So that's the orbital angle, how orbital angular momentum leads to this magnetic energy. But I said this whole discussion has been motivated by the fact that we have this thing called spin, which is not related to rotation necessarily, but related to the magnetic property of the particle itself. So if the particle is not just spinning around, but the particle is just sitting there, its spin quantum number is going to be related to how much magnetic energy is involved. But we should have the same kind of angular momentum mathematics for spin. So for the spin magnetic moment, in that case, what we have is a magnetic moment related to spin, which should be a gyromagnetic ratio times the spin vector. Just all we're doing here is replacing the angular momentum, the orbital angular momentum operator, with a spin, quote unquote, angular momentum. I can put a S here to kind of differentiate between the orbital angular momentum magnetic moment and the spin magnetic moment. Anyway, the gyromagnetic ratio should be the same. It should be minus, it should be the charge of the particle, Q, divided by 2mc. Okay. Now, as it turns out, the spin actually has a much larger gyromagnetic ratio. So we actually throw in a kind of a normalization factor. So I would rewrite this as G times gamma times the spin operator. So I have this G factor, which kind of shows how we're boosting the strength of the magnetic moment from the to the gyromagnetic ratio. So if we wrote down our interaction Hamiltonian, again, it'd be minus mu sub s dotted into B, which I can write down as the magnitude of it being G Q over 2mc, the spin dotted into the magnetic field. Now, if we rewrite this in terms of Pauli spin matrices, then this would really be G, the charge, H bar over 2mc, the Pauli spin matrix, dot B. Actually, I should be careful. It's not 2, but 4, because the spin operator is H bar over 2 times the Pauli spin matrix. So there should be an extra factor of 2 in the denominator of that. Okay, so but we know what the Pauli spin matrices look like, and so now we could just throw those into the equation to calculate the interaction energy. So therefore, if we compare things when it comes to spin, then the magnetic moment, this magnetic moment that we've been calculating, is G over 2 times this gyromagnetic, I'm sorry, not that, G over 2 times the Bohr magneton. So again, like I said, it's this factor we're throwing in to increase the strength of the magnetic moment. So where does this factor come about? Well, it turns out where it comes about is that if we were to treat this problem relativistically, then we would have to use something called the Dirac equation, which we're not going to do in this video. But what the Dirac equation does that something like the non-relativistic Schrodinger equation can't do, it is basically to calculate this G factor. And so from theory, the Dirac equation predicts a G factor of 2, and I'm going to emphasize this exactly. So there should be a value of 2 coming from the derivation of the Dirac equation of an electron, a relativistic, a fast-moving electron in a magnetic field. Turns out that the experimental value so if you were to do an experiment of having an electron and putting it into a magnetic field, what you would get for this extra factor is 2 times 1.0011596524 plus or minus a 20 on the end of it. So this G has actually been measured to, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places with an error on the last 2 decimal places. So this is a fantastic measurement with tremendous precision involved. So if you look at this, Dirac predicted that G factor should be 2 exactly, no decimals on it whatsoever, experiment says it deviates from 2 in the 3rd decimal place. So that's pretty, I mean, that's a pretty good measurement. But it deviates from it, and we've been able to measure it now to 10 decimal places. So it's not like there's an error involved in here. And so the question is, where do all these other decimal places come from if Dirac derived it to be exactly 2? And it turns out that these are quantum mechanical corrections that you would get if you were to use Feynman and Schwinger and Tomanaga's quantum electrodynamics. So if you use quantum electrodynamics, or QED, what you would find is that you would have just an electron flying through outer space, which would give you a value of 2, like Dirac predicted. But if you now add to this that when the electron is flying through space, a virtual photon is emitted and then reabsorbed, plus, as the electron flies through space, another virtual photon is emitted and absorbed, and then a second virtual photon gets emitted and absorbed, and you can do this, for infinite number of virtual photons, and you can add to this the case where you have a virtual photon emitted, which then produces a electron-positron kind of bubble. So electron-positron are created, which then annihilate back into a photon, which then leaves us with the electron. And then you can come up with even more of these cases where a photon's emitted, becomes electron-positron pair, annihilates into a photon, but in the process another photon gets created, which leaves the positron and goes to the electron. So you have all these virtual particles, this cloud of particles being created from the energy in the vacuum and then basically annihilating back into pure energy again. And when you start adding those up, what you get is G, which is equal to 2 times 1 plus the fine structure constant divided by 2 pi plus other factors on the order of the fine structure constant squared plus factors of the fine structure constant cubed, the fine structure constant to the 4th power. And these terms of the fine structure constant come about because you would get these virtual photons, these virtual electron-positron pairs being created. And so eventually you just keep adding up those terms, and what you get is that number now calculated from theory of 2 times 1.0011596,517 plus or minus 22, calculated from theory. So the theory now gives us a value which is this, and compared back to the experiment, the experimental value is 1.0011596,524 plus or minus 20. So the theory now can predict all the way up to the last 2 decimal points in the number. So this is like the crowning achievement of quantum mechanics, about the fact that we have this theory which calculates all of these particle interactions and is able to calculate this G value for the magnetic moment from spin to amazing precision. And this is the most precise theory in all of physics.